Welcome to this training session for the software SILDIS Module 1B for the prediction of acoustic and aerodynamic performance of reactive silencer. For the simulation of a single expansion chamber without perforated tubes, as per example 1B.4.2 of user's manual. The expansion chamber is made of 5 elements numbered 2 to 6 from downstream side towards upstream side, with number 6 being a uniform tube for inlet, number 5 being an extended inlet, number 4 being a central uniform tube, number 3 being an extended outlet, and number 2 being a uniform tube for outlet. Worksheet in Koala 1B deals with generalities. The software SILDIS being Excel based, we can modify cells being either yellow like this or being a drop down menu like this. The green flags are highlighting cells to be modified for our present application. We can enter a temperature 500 degrees here, a pressure 100,000 pascals here. We can enter one here as we are going to enter sound power levels per 1 octave frequency band and not 1/3 octave frequency band. And we can enter those sound power levels here. In COSIL 1B is the main worksheet for the silencer configuration. We can enter a mass flow rate here, 0.1 kilograms per second. The density we can find here for an easy conversion. We can enter the inlet diameter of the silencer, 100 mm here, and we can select models relating to the self-noise here. A general model of flow acoustic power among a drop-down menu list, a model for thermodynamic correction here, a model for spectral correction here. The existing model selection is the best compromise that the user can, however, modify whatever the reason. The mounting we can select here among this drop-down menu list are expansion chamber being referred to as EC1 in this library. We can find here a sketch allowing to find the elements selection already discussed. Here we can select a reactive chamber, which could also be dissipative. In this case, the output results of module 1 should be used as input data for the present module. As soon as we have selected the mounting EC1, the appropriate elements arrangements are shown here, with the elements number being highlighted in red and with the corresponding matrices and parameters. Group, subgroup, diameters, eventual offset for elliptical geometry, number of tubes in parallel, sub-inlet diameter, geometrical length, model for transmission loss, roughness, model for total pressure loss, and also information related to end correction. All of those parameters are going to be refreshed depending on the input data to be entered later. To help, some pictograms are displayed here for each element, and using the key, which is here, one can see that number 6 is a uniform tube, number 5 an extended inlet, number 4 a uniform tube with the biggest diameter, number 3 an extended outlet, and number 2 a uniform tube. Could be also, depending on the case, a side inlet, a side outlet, a transverse inlet, a transverse outlet, or a variable tube in case of elliptical geometry. Could be also a reversal expansion or a reversal contraction in case of overlapping tubes. Could be a Helmholtz resonator with a lateral branch, and could be also a concentric resonator with perforated tubes. In case of circular cross-section, ds is the smallest diameter, dl is the larger diameter, and we can enter here for the stage 1, 0.1, which is entered by default. For the smallest diameter, 0.3 for the biggest diameter, 1.2 meter for the chamber total length, and 1.5 minus 4 for the tube's roughness, which is a usual value set by default. Here we find again the highlighted elements of our mountings numbered from 2 to 6. 2, 4, 6 are uniform tubes. 5 is the extended inlet, and 3 is the extended outlet. All the dimensions relating to diameters are displayed here automatically. And what we need to enter is only the geometrical length. For this, the software is displaying the dimension, allowing a tuning of the chamber to optimize the performance. This value we should report here for the extended inlet, for the extended outlet, and also for the inlet uniform tube and for the outlet uniform tube. The length of the central tube being computed accordingly. Here we can select the total pressure loss model for all elements. appropriate models being selected by default depending on the type of element. Finally, we have to select end corrections for the stage 1 inlet and stage 1 outlet as highlighted in green here. For example, we can select for both a termination connected coaxial model here and here. Now we can switch to worksheet EC1, displaying all the dimensions of the expansion chamber as entered to check that what was entered is relevant. The upper sketch is displaying geometrical length, whereas we have also a sketch for added length and corrected length. This could be the same in case of other mountings if selected. In-out CODIS 1B is the final worksheet displaying the results. We can find here all the input data entered, and we can select for the performance indicator without self-noise between transmission loss, insertion loss, or noise reduction. What we've got here is the performance indicator, in this case sound transmission loss, as a graph from 10 Hz to 10 kHz, and also with a zoom for low frequency. 1/3 octave band and 1 octave band are computed, as well as an overall A-weighted value with respect to the reference spectrum entered. LW0 is the unsilenced sound power level. LW1 and delta L without consideration of self-noise or with consideration of self-noise are illustrating the situation with the silencer accounting the self-noise LW. The total pressure loss is also computed for each element and also as the total for the silencer. That's all for this training session. Thank you very much for your attention.